Alright, first up we want to use the packet that I gave you last time. Calculating equilibrium constants. Alright, so first thing that we want to do is write the KC. Now you'll notice as we go through K, KQ, KC, KP, KA, KB, there are tons of Ks. They all are set up the same, okay? They can only have aqueous things in them, or gases. They cannot have solids or liquids ever. Okay, so solids or liquids just drop out. Okay, so as we're writing KQ, we're going to write K, whether that's for KC or KP. KC is a K of concentration, KP is K of pressure, Ka is K of acids, Kb is K of base, Ksp is K of solubility. They're all written the same. Okay? Alright, so on this one we're going to have products of reactants. So Kc here is equal to, and I think I went that again, Kc is equal to the concentration. And before we do this, what is one of the things I need to make sure that is true? That is balanced. Is it balanced? It is not balanced. What's off? A hydrogen. So what do I need to put in front of the hydrogen on the left? 3. Right? Okay, so now we can do it. So CH4, and it is to 1 power, so we don't write it. H2O, to 1 power, we don't write it. Divided by CO, and H2 to the 3rd power. Now, they've given us several data, and we just do a plug and chug. We throw those in, and we find the Kc value. So I'm going to give you a few seconds. I want you to plug and chug, figure out what the Kc value is for each of these, and then calculate the average. You guys know how to do average, right? Add those two together, divide by 2. Okay, so take 10 seconds and do that. Okay, as we look at this, a couple of things we need to know to be able to answer the next question. If K is bigger than 1, then it's going to go forward in the reaction. Word. If K is the other way, less than 1, and it would have to be bigger than 0, but less than 1, then it's going to go reverse.
Why did you do?
Just means, like when I need 2 signs, I really don't, but usually K, when it goes forward, very forcefully, is very large. Okay, so this is bigger than 1, but not very much bigger, so we're probably going to get a forward reaction, but it's not very forward, it's sort of slow. You know, some reactions go forward, but they're not necessarily fast. Okay.
Wait, why is it going forward?
Because it's bigger than 1. If it's less than 1, but bigger than 0, then it's going to go reverse. Okay, I want you to take a second. I want you to do the next one by yourself. See if you do it.
Products are always on top, right?
So make sure you have your, remember the brackets represent moles per liter. So make sure you have your moles per liter when you plug it in. Okay, let's look at this. Whenever you do a K expression, you have to have a balanced equation to start with. So the balanced equation first, that was pretty easy. You do products over reactants to their coefficients, and then you make sure that whatever you've got is in liters. On this particular one, the liters would actually cancel out because they got the same on the top and on the bottom, but that's not always so. So when you have brackets, make sure you're in molarity. And that's what we did here. We just took on this area right here, you're just taking your moles divided by the 2 liters, your moles divided by 2 liters, moles divided by 2 liters. And you got these concentrations, which is capital M, which means moles per liter. Okay? And then to calculate the Kc, that's what we got from right here. Now, is it a forward reaction or a reverse reaction? Is it very forward or just barely? Just barely. Okay? And we ask what happens if we add more carbon. Well, if we add more carbon in here, then that bottom number is going to get bigger. That means the overall number is going to get smaller. And then for the reverse reaction, remember that on thermodynamics, when we reverse reaction, what do we do to delta H? Or we change the sign, right? We just went positive and negative. With KQ, you have to flip it, literally. So KC, to go backwards, you go 1 over KC, and this is the reverse. It's not equal. And this is the reverse. So whatever you do, if you're going forward and you got a KC, then to go reverse, you go flip it that way. Okay? So you got to remember that. A little bit different for this. Okay, let's go on to the next page and see what we can do. The next couple pages should be about the same. Now, pressure, KP is just K of pressure. You're doing the same things, plugging in the same way. But if they don't give you something, let's do this next one. Guess what? It starts getting into the problem-solving mode. When they don't give you everything and you plug stuff in to try and find what you don't have. So on this equation up here, first up, is it balanced? It is balanced. Okay, and we do know, I notice here, we do know the KP value. Okay, so that's something we didn't have before we were solving for KP. We also have that enough solid PCl5 is placed in the ball. So this right here, you know, I can't read it right very much as a solid. That means it's going to be in the K expression or not?
This is gas.
Is it a gas? Oh, is this one a solid?
They're all gases.
They're all gases. Okay, well, then we're going to go on from there. Okay, so we're going to write a KP expression. So KP to this balanced equation is what?
CO2.
Now, when we do pressure instead of concentration, this is how we write it. PCl3 times pressure of chlorine divided by pressure of PCl5. Now, if we had to square it out, we'd still do the big P as squared or cubed or whatever. But that's how you write pressures. So concentration is in the brackets, pressures with a capital P for pressure. Okay? So we can put in...
How come there's not a double P on the second paragraph?
Yeah, there's no phosphorus. Okay, so now we're going to plug in what we know. We know that this is equal to 0.0415, right? We also know, what else? We know PCl5 here. So we know that PCl5 on the bottom is 1.50 atmospheres. Now, whatever I have of this is going to break down, and I'll get one of these and one of those, right? So I can put here an x squared, and I can solve for x squared. So to plug through, solve for x squared, let's see what the pressure for PCl3, which is equal to the pressure of PCl2, is. Okay, what do we get? 0.2. 249, and this would be an atmosphere's 24. So 250. Okay. All right. So now on the next one, number 3, whose law is that? It's Dalton's. Dalton's Dell law, which was all the partial pressures add up to equal pressure total in the flask. So PT is equal to pressure 1 plus pressure 2 plus pressure 3. So guess what? To get total pressure in flask, I'm going to take 1.5 plus 0.25 plus 0.25, and that will give me what for the total? 2.00 atmospheres for the total pressure in the flask, and I'm not going to circle it. Okay, going down to question 4. What was PCl5 before the dissociation occurred? The pressure. So if I go back and I put all of it back into the reactants, what was the pressure of PCl5 before it dissociated? 2.
Oh.
Because I had no product. Okay? And what fraction of PCl5 has dissociated? So to get the dissociated, we've got yes, it's that simple. It's that simple. So 1/4 has dissociated. Okay, or 25%. All right, what I'd like you to do is, I believe on most of these others you can go backwards and forwards, but let's skip to that last page where there's a relationship between Kc and Kp. We have an equation. This equation is given on your list of equations that you'll be given, and it tells you how to go back and forth between. So if I've got Kp but I need Kc for an equation, then I can figure it out by doing RT. Now R is one R that we already know, which is what? Yes, law R. Good, 0.0821. Times the temperature times the change in moles from the reactant to the product. So if I'm on the reactant side, say here, this would be 5 moles and this would be 2 moles, so the difference would be 3. You see how that works? That's how I get delta N. Okay, just look at the coefficients. Okay, so here I got 5, here I got 2, difference from one side to the other, that gives me delta N. So I just throw it in and I can go back and forth between Kp and Kc. Alright? And that equation is on there. So, I'm going to, whoa, hello. Let's just throw this around, okay? Because it's fun. I'm going to let you have some time to figure the rest of the sentence and work on it and ask questions. Down at the bottom of that is Le Chatelier's principle. We were working with Le Chatelier's principle in class last time with the lab that we were doing with equilibrium. Okay, it's basically saying if I put a stress on a system, then that system is going to react to relieve that stress. Okay, it's going to come back to a new equilibrium. So you noticed is if you got to an equilibrium moving the water, and you got to the same level, and then you had to take some out and go back until you hit a new level. It was different, but you still hit an equilibrium. It was the same going back and forward. Okay? So I'm going to let you work on this. I'm going to let you work on your lab notebook. Oh, except hold off on doing the very back page. We're going to talk about ice next time. I don't want to bring in ice yet. I want you to get used to doing the rest of the stuff, and then we'll talk about ice. We're gonna finish. Let's see where we get the rest of today, and then we'll do that last problem on the intermediate next time. Okay?